De Broglie's explanation of Bohr's second postulate of quantization. Bohr's second postulate states the angular momentum of the electron orbiting around the nucleus is quantized. That is, Ln is equal to nh upon 2 pi. N is equal to 1, 2, 3 and so on. Equation 1. It is quite puzzling that why should the angular momentum of the electron have only those values that are integral multiples of h by 2 pi? De Broglie realized that if you consider the wave nature of the electron and assume that an integral number of wavelengths must fit in the circumference of an orbit, you get the same quantized angular momenta that Bohr did. We know that in a string, standing waves are formed when the total distance traveled by a wave down the string and back is one wavelength, two wavelengths, or any integral number of wavelengths n lambda. For an electron moving in nth circular orbit of radius Rn, the distance traveled in one revolution is equal to the circumference of the orbit is equal to 2 pi Rn. According to De Broglie, 2 pi Rn is equal to n lambda. N is equal to 1, 2, 3 and so on. Equation 2. Figure shows a standing wave on a circular orbit for n is equal to 4. That is, 2 pi r4 is equal to 4 lambda, where lambda is the de Broglie wavelength of the electron moving in this orbit. The wavelength of a particle wave having momentum p is given by relation lambda is equal to h by p, equation 3, where p is the magnitude of the electron's momentum. If the speed of the electron is much less than the speed of light, the momentum p is equal to mvn. Thus, lambda is equal to h upon mvn. From equation 2 we have 2 pi Rn is equal to nh upon mvn gives mvn Rn is equal to nh by 2 pi. This is the quantum condition proposed by Bohr for the angular momentum of the electron. The quantized electron orbits and energy states are due to the wave nature of the electron, and only resonant standing waves can persist.